Modern flight is defined by the massive, violent expenditure of energy. To overcome gravity, we rely on combustion, burning tons of liquid fuel to generate the thrust necessary to keep heavy machines in the sky. In 1670, a Jesuit mathematician named Francesco Lana de Terzi proposed an alternative that required zero fuel. He envisioned a wooden boat suspended beneath 4 hollow copper spheres, designed to rise into the sky without wings, oars, or fire. The logic followed Archimedes' discovery. An object immersed in fluid experiences an upward force equal to the weight of the fluid it displaces. If you could pump the air out of those spheres to create a vacuum, the vessel would weigh less than the air around it and float. Lana de Terzi eventually abandoned the project, fearing it would become a weapon for aerial bombardment. However, even if he had attempted to build it, his copper spheres would have imploded. And materials of the 17th century could not bridge the gap between structural strength and the lightness required for buoyancy. This failure established a paradigm that has lasted for over 2 centuries. Because a vacuum vessel built as a sphere cannot survive atmospheric pressure, aviation shifted toward the hypercomplexity of jet engines and the constant consumption of fuel to maintain lift. The engineering obstacle is known as the buckling paradox. To be light enough to float, a sphere's walls must be paper thin. But the atmosphere at sea level pushes inward with 10 metric tons of force per square meter. A shell thin enough to rise is too weak to resist that crushing weight. In 1915, German engineer Richard Zoeli provided the mathematical proof of this impossibility. His equation for the critical buckling pressure of a spherical shell showed that for any common structural material, the geometry would collapse before it ever achieved buoyancy. Take a sphere made of aluminum. For it to float, the walls must be only a few micrometers thick. At that scale, the Zoeli equation predicts the structure will collapse at a tiny fraction of the required load, resulting in a safety factor of 0.0015. Engineers spent generations attempting to overcome this with better materials, testing everything from titanium to advanced carbon fiber composites. But every attempt at a spherical vacuum vessel ended in the same explosive collapse. These failures were a result of a category error. Designers assumed a vacuum vessel had to be a continuous curved shell, similar to a submarine. The geometry of the sphere itself was the trap. Solving the paradox requires moving outside the shell paradigm and into a tetrahedral lattice architecture. A curved shell resists pressure by bending, leading to buckling. A tetrahedron, however, resolves that atmospheric pressure into pure axial compression along its straight edges. The struts are pushed or pulled from the ends, with no bending in the structure. This shape change shifts the governing physics to a formula published by mathematician Leonhard Euler. Using carbon fiber struts in this tetrahedral configuration allows the structure to carry the atmospheric load, while a thin, loose skin simply seals the gas.
The math shows the safety factor jumping from 0.0015 to 6.3. This approach decouples the structural burden from the gas containment. The lattice handles the pressure, the skin holds the vacuum, and a shape known to Euclid finally provides the rigidity a sphere cannot. Theoretical safety factors are only an argument. To prove the physics of vacuum buoyancy, that math must be translated into a physical object that rises into the air. The Moonball was designed as the baseline proof, a 3D printed hollow tetrahedron only 74 millimeters long. At this small scale, the physics of flight are incredibly difficult because the structure's weight is very high relative to the displaced air. Building a micro-scale vacuum vessel usually requires expensive industrial pumps and specialized valves. To make the proof accessible, the process was redesigned to work in a common kitchen. This is the thermal vacuum hack. Heating the Moonball to 327 degrees Celsius causes internal air to expand and escape through the porous printed walls. At peak heat, a steel ball bearing is dropped into a valve to seal the tetrahedron. As it cools, the internal pressure drops to 26% of the atmosphere. The internal cavity displaces enough air to overcome the mass of the shell. When the Moonball hovers above the counter, it demonstrates that vacuum buoyancy is a problem of geometry rather than a limitation of physics. Because volume increases at a cube, while surface area only squares, the larger this structure becomes, the more lift it generates. A solution to a 242-year-old problem is a target for patenting and institutional enclosure. Traditional aerospace structures are often locked behind paywalls or corporate secrecy. To prevent this, the creator recorded mathematical proofs, thermal protocols, and CAD files on the blockchain. This established a permanent, time-stamped record of the technology. By placing this data on a public ledger, the foundational architecture of tetrahedral vacuum flight became immutable prior art. It is now legally impossible for any corporation to patent or claim ownership over these core geometric principles. The information was released into the public domain to ensure buoyant flight is no longer restricted to those with institutional credentials or government funding. The same scaling laws used for the 74mm Moonball apply to structures measured in meters. The neutral cell challenge asks builders to prove this at a 3-meter scale. Participants build a geodesic lattice using off-the-shelf carbon fiber arrows and mylar film. Materials are accessible to any workshop, university engineering club, or independent builder. A sphere of this size displaces 14 cubic meters of air. As the internal cells are evacuated, the gross lift rises to 17 kilograms.
The objective is reached when the digital display on a load cell reaches 0, signaling that the structure is neutrally buoyant. For centuries, flight was synonymous with combustion because we were constrained by geometry of the shell. This transition to a tetrahedral lattice suggests that lift can be achieved through calculation and geometry rather than fire.